Welcome to geometry class. Today we'll talk about perpendicular bisectors in triangles. Remember, a perpendicular bisector is a line or ray or segment that intersects a given segment. In this case, we have segment AB. Intersects a given segment at a right angle and divides it into two congruent segments. So here, this line, maybe this is line L, is the perpendicular bisector of segment AB. We need to talk about perpendicular bisectors in the context of triangles. First thing we need to talk about is the perpendicular bisector theorem. It says if a point is on the perpendicular bisector of a segment, then it is equidistant from the endpoints of the segment. We'll take a quick look at that and work through a very informal proof of the theorem. Suppose we have a segment here, we'll call this segment AB. And suppose we have this perpendicular bisector. The theorem says that any point on this bisector, for instance, point C down here, will be equidistant from A and B, or from B and A, meaning these segments are congruent. A point up here, we'll call this point D, also equidistant from A and B. Any point on that perpendicular bisector will be equidistant from the endpoints. Instead, we prove it quickly. Let's just take a look at that. Again, suppose we have segment AB and a point on the perpendicular bisector, such as this point right here. Let's not worry about its name right now. If we connect this up as a triangle, here we go. We actually have two triangles here, one on the left, one on the right. And you can see by the reflexive property that this segment is congruent to itself. Therefore, by side, angle, side, we have two congruent triangles. CPCTC tells us that these sides must be equal as well. That is congruent. And so we find that whatever this point is, wherever it is, it must be equidistant from points A and B. Converse of the perpendicular bisector theorem is similar. It says that if a point is equidistant from the endpoints of a segment, then it is on the perpendicular bisector of the segment. What does that look like? Suppose we had, again, a segment, call it segment AB, and we had another point down here, we'll call that point C. Suppose that we knew that point C was equidistant from B and from A like this. You may look at that and recognize that it's an isosceles triangle, and therefore the base angles are congruent. We can draw in a segment here through the midpoint of AB to point C like this. And because that's the midpoint, we can be sure that these segments are congruent. And so I think you can see by side, angle, side, these two triangles are also congruent. That is, triangle AMC and triangle BMC are congruent. If those two triangles are congruent, that means that these two angles are congruent. And since they're a linear pair, we know that two angles that are a linear pair and are congruent must be 90 degrees. Therefore, since we already determined that M is the midpoint, and now we know that these two lines are actually perpendicular, we can be absolutely certain that MC is in fact the perpendicular bisector of AB. So we have these two theorems that help us when we're dealing with perpendicular bisectors or points that are equidistant from the endpoints of a segment. We need to go a little bit deeper with and actually talk about this in the context of triangles. Before we do that, we need to introduce this word concurrent. We say that when three or more lines intersect in one point, they are concurrent. So, for example, if I have a line here, call that line L, and a line here, call that M, we say the point of intersection is this point in here. We could just call that O. So we've got these two lines intersecting at a point, and there's really nothing too special about that. But if a third line were to come through here and also pass through line O, and I'm sorry, it passes right a little bit, but also pass through line O, we'll call that line N, we would say that these three lines are concurrent at point O. We call that the point of concurrency. For any triangle that exists, there are four different sets of lines that we are interested in, which are concurrent at different points. We will look at them one at a time. The very first point we'll look at is called the circumcenter. Circumcenter. Circum, by the way, means around, as in the words circumnavigate, to go around the globe, or circumscribe, to write around, or circumvent. Perhaps if there's a problem, you may circumvent it. Circum means to go around. And so we'll look at that word in this context. Circumcenter theorem says that the perpendicular bisectors of the sides of a triangle are concurrent at a point equidistant from the vertices. That's a lot to get your head around, so let's see if we can break it down a little bit. First of all, the perpendicular bisectors of the sides of a triangle. What are those? If we have a triangle, and we talk about the perpendicular bisectors of the sides, let's just identify the midpoints here. And again, this is just a rough sketch for now. We want to identify the perpendicular bisectors of each of the sides. So here's one of them. Here is another one. And here is the third one. Those are the perpendicular bisectors. I've sketched in really, the three perpendicular bisectors of the sides. Notice they all pass through this point right here. That is the circumcenter. Okay, that's the circumcenter. Now, the theorem says that the circumcenter is equidistant from the vertices. That means that if I were to draw in the additional segments here, here, and here, that this circumcenter is equidistant from all of those. The sketch is not exactly a picture of clarity. We'll look at a construction in just a moment, and that will help us to see what we're talking about. Circumcenter is the center of a circle which can be circumscribed about a triangle. Again, let's go ahead and look at the construction right now and think we can make sense out of that.
Now we'll construct the circumcenter of a triangle. In order to do that, we need three tools. We need a compass, we need a straight edge, we need a pencil. Remember that the circumcenter of a triangle is the point of concurrency of the three perpendicular bisectors, that is, the perpendicular bisectors of each side. So before we do the circumcenter, let's just review how we construct a perpendicular bisector. I'll just start with a random segment here, so we have something to look at. We'll call it segment AB. And we need to construct the perpendicular bisector of segment AB. To do so, we take our compass, and we want a fairly large setting. It has to be at a minimum more than half AB. This particular setting I have here is almost the same as AB. That's okay. We'll swing an arc above and below, change points over to point A, cross above, and cross below. All right, now what we need to do is connect these intersections of these arcs above and below. And there's our perpendicular bisector. So we can be sure this is a 90-degree angle, and these segments are congruent. In order to construct the circumcenter, I'll just begin by drawing a fairly random triangle here, such as this one. It's an acute triangle. We'll label these vertices A, B, and C. And then in order to do this, we just need to construct the perpendicular bisector of each side. So we'll start with AC, and we'll put an arc on one side and on the other. And then we'll move to point C, cross that arc, and cross that arc. There's our first perpendicular bisector. That's at a right angle. Those are congruent. Let's move to segment CB, or side CB. Cross arc above, arc on the other side. Move over to point C. Cross the arc on one side and cross on the other side. And this is our second perpendicular bisector here. And then finally, let's identify the perpendicular bisector of side AB. Again, point of our compass, we put an arc on one side, arc on the other side, arc there, cross, and cross that arc there. And here is our third perpendicular bisector. There we go. So our circumcenter is here. It'd be nice if I could spell it right. There's our circumcenter. Notice again that our circumcenter is equidistant from the vertices. That's important to remember. It's somewhat definitional. If we ask the question, circumcenter, what does it mean? Circumcenter, circum means around, center means center, of course, the middle of, if you want to define it that way, equidistant from these different points. And the circumcenter is the center of a circle that can be circumscribed. or drawn around the circle. So let's just take a look at that real quick. If we swing this circle around, you can see that that circle goes around. And this point, the circumcenter, is equidistant from each of these three vertices. So we find that a circumcenter is the point of concurrency of the perpendicular bisectors, and that it's equidistant from the vertices.
Okay, we've taken a look at the construction. Now let's just see if we can make a practical application out of this. Here's a problem. It says a development company wants to construct a new mall. Based on statistics which they've reviewed, the company concluded that the mall should be equidistant from 3 cities, Boston, Worcester, and Providence. How can the company find the location which is equidistant from those 3 cities? Well, in order to solve the problem, let's identify the triangle that has vertices at Worcester, Boston, and Providence. That's the triangle we're interested in. So it's probably fair to say that the locations will be somewhere in the middle of those. But the way that we'd find it, the way that we'd solve this problem, is by identifying the perpendicular bisectors at each of those sides. There's 1. There's 2. And of course, we would do this with much more precision. There's 3. Those are the perpendicular bisectors. And you'll find that this in here is the point of concurrency. And that's where we would locate them all. Notice that depending on the type of triangle we have, the point of concurrency may show up in a different place here when I talk about the circumcenter. For instance, if I sketch in these perpendicular bisectors, you'll find the point of concurrency is actually down here someplace. I'd encourage you to work through the construction a couple times. Particularly, it may be a good idea to try your hand at an obtuse triangle and see where your circumcenter ends up. You might want to try it with a right triangle as well, certainly with an acute triangle, and just see how that circumcenter moves around depending on the shape of the triangle. As always, if you have any questions, please send me an email.